You're here because you want to master alkenes with a University of Cambridge graduate. Let's begin. Your school is going to yap so much about alkenes, and you're going to feel lost and even confused for this topic. Well, I'm here to summarize all the critical points you need in this short video so that you can learn alkenes from this video and even use this for reference for your revisions as well. Alkenes is a pretty loaded chapter, but what's essential for you to take away is the different reagents and conditions that you have to memorize for the different reactions involving alkenes, the main reaction mechanism involving alkenes, which is electrophilic addition, as well as the different reasonings behind the different reactions itself. So alkenes are unsaturated hydrocarbons that are mainly characterized by this C double bond C. So if you see a C double bond C, your instincts should instantly kick in and figure out that, oh, this is testing me on alkenes, so I have to use my alkene knowledge if the reactions involve this double bond. Because of this C double bond C, it's going to be sp2 hybridized for the carbons involved in this C double bond C, and it's going to be trigonoplanar about these carbons. For nomenclature, just refer to my Intro to Organic Chemistry lecture so that you understand how to name your alkenes. The key isomerism to take note of for alkenes is cis-trans isomerism. And this is because, as I've run through in my Intro to Organic Chemistry lecture, the alkenes have a C double bond C, and this double bond has restricted rotation. Refer to my lecture here to understand more details if you forgot about cis-trans isomerism. For physical properties, you will also be expected to compare the melting points or the solubilities of your different alkene molecules, but just refer to my chemical bonding lecture because that lecture covers all the key concepts that you need to know for determining physical properties or comparing between different molecules. So what are some of the different ways to prepare my alkenes? Well, you have cracking of alkanes, which is splitting my large alkane molecule into many small fragments. So for example, you can have C8H18 that is split into C4H8 and C4H10. And because of this, you would form an alkene and an alkane. And this is done by very strong heating of your large long chain alkanes. Next, we have the dehydration of alcohols. So this is involving an elimination reaction of H2O from your alcohols. What's going to happen is, for example, your propanol is going to be dehydrated and you're going to form your alkene over here with H2O as, of course, the side product. The reagents and conditions are any one of these. So you can either use excess concentrated H2SO4 with 170 degrees Celsius. You can also use Al2O3 solid with 350 degrees Celsius. Or you can also use concentrated phosphoric acid with 200 or to 250 degrees Celsius. Again, I must emphasize, you need to memorize all your reagents and conditions. You can be tested on any one, and these are literally free marks. Don't miss out on these. Next, we have elimination of HX from your halogenal alkanes. So you can have, for example, a halogenal alkane here, and you're going to form your alkene with the HX, where X is either a Cl or a Br involved. And this is usually done with ethanolic NaOH or KOH, and you need to heat it under reflux. So for elimination reactions, for example, dehydration of alcohols or the elimination of HX from your halogenal alkanes, you need to understand this rule in order to predict the different products from your elimination reaction and predict which one is the major product and which one is the minor product. This is Sizev's rule, which states that the more highly substituted alkene is more stable, and therefore it would be the major product. And how you determine who is the more highly substituted alkene is to look at the number of R groups attached to the double bonds. So if you look at this example over here, you can see that there are two products that can be formed. Either you eliminate this H with X over here to form the product on the right, or you eliminate this H over here in red with the X to form the product at the bottom. So how do we predict which is the major and which is the minor product? The first step is to always draw the alkenes that are formed from the reaction. And then you can look at the alkenes, so the carbons involved in the C double bond C, And look at the number of R groups that are attached to these carbons. So we have one R group and you have two R groups over here. Whereas for the bottom product, if you take a look at these two carbons, you only have one R group over here. And because of this, the major product would be the one on the top because it has two R groups attached to the whole alkene, and the bottom one is the minor product. Another side note is that trans alkenes are also more stable than your cis alkenes. And therefore, if you had to choose between the two products, you would produce more trans than the cis. And the reason for this is because the R groups of your cis product is spatially closer together, and therefore they will experience more steric hindrance and electron repulsion. Because of this, you would form this product more than the cis one, if ever you have the same number of R groups attached to the alkenes. Now on to the different reactions that alkenes can go through. The first is combustion, which all the organic reagents can go through, so just refer to my mole concept video to understand the calculations and equations involved for combustion questions. Next, we also have reduction, so your alkenes can become alkanes. And this is with the use of hydrogen and with a catalyst. So for my reagents conditions, I can use any one of these. So either H2 gas with nickel with 200 degrees Celsius, or H2 gas with platinum at RTP. RTP is room temperature and pressure. I'll use this phrase a lot. Or H2 gas with palladium catalyst and RTP. And the unique thing about these catalysts is they are heterogeneous catalysts. If you forgot what heterogeneous catalysts are, do refer to my reaction kinetics video where I explain how heterogeneous catalysts work. These are just sticky surface catalysts that help to lower the activation energy involved for your reaction. Now on to the main reactions of alkenes, electrophilic addition. And the basis for how electrophilic addition works is because these alkenes are highly reactive for these reactions due to the pi electron clouds for the C double bond C. You can imagine this pi bond is a whole pi electron cloud. And this is an electron-rich site that will attract your electrophiles, who are mainly electron pair acceptors. So what are some typical reactions of electrophilic additions? Well, we have hydrogen halides. So this is just as expected of addition reactions. You're just adding the HX across the double bond. And that's how you get your product. The reagents and conditions are gaseous HCl/HBr/Hi at room temperature. Next is the electrophilic addition of halogens. So same principle, you're just adding the X2 across the double bond. And the reagent conditions are Cl2 or Br2 in CCl4. And it must be in the dark. And this is because you don't want FRS to be a possibility for this reaction. Do take note that if it is in a nucleophilic solvent, your reaction products could be different, and I'll explain using this mechanism later on. Next, we have electrophilic addition of water. So we're just adding H2O, so H and OH, across the double bond. So the reagents and conditions are concentrated H2SO4 cold, and then adding H2O warm. Following up, you have to understand the mechanism behind electrophilic addition. The first step is the pi electron cloud in your alkenes is going to move to the electrophilic side over here. And this is because hydrogen here is less electronegative than your Br. Again, it's important to state all these delta pluses and delta minuses to show that you understand this concept. And then the electrons within your HBr bond is going to move to the electronegative region, aka the Br atom. And then the reaction is going to produce a carbocation, which is this guy over here, and also the Br minus. And also take note that this is a slow reaction. Next up, your carbocation is going to get attacked by the electron-rich Br minus by the lone pair. And that's how you form your product. Do take note that this is also a fast reaction. It's also important to understand this rule called Markovnikov's rule, which is important in predicting the major or minor products from your electrophilic addition reactions. So what this does is, if you look at propene, your hydrogen and your hydrogen halide can either come in the middle position or in the right position over here. Now, if we take a look at both the carbocations that comes out from this reaction, you will see that one is more stable than the other because this top one has two R groups, 1, 2, attached to the carbocation, versus the bottom one is a first degree carbocation because there's only one R group that is attached to the carbocation. And we know that R groups are electron donating groups that will help to stabilize your carbocation. So more R groups means more stable and therefore more preferentially formed. Therefore, the top path is the major path and the bottom path is the minor path. So looking at the products, you can predict which one is the major and which one is the minor product. So going back to my electrophilic additions of halogens, remember that if it's in a nucleophilic solvent, the first step always involves the addition of the electrophile. So in this case, you add one of the X's. And then after that, because the nucleophilic solvent is very in excess, the solvent is actually going to be preferentially reacting and attacking the carbocation over here. In this case, if I use water for example, the water is going to attack with the O lone pairs to the carbocation. And because of this, you are going to form a different product over here. Also important to know is that your F2 is not really used in electrophilic addition reactions because they are too reactive, they react explosively, and your I2 is also not being used because they're just too unreactive. Now moving on to other reactions that alkenes can go through. Alkenes can also go through oxidation. So a very popularly asked one is mild oxidation, where your alkene just has two OH added across the double bond. Very, very good distinguishing test for alkenes. Now do remember in your equation that you have to balance your equations appropriately. For the reagents and conditions, you can use any one. The key point is that you need to put it in a cold temperature and use the oxidizing agent, which is KMnO4. If you put it in an alkaline medium, which is for example NaOH, you are going to get decolorization of your purple KMnO4 and also the formation of your brown PPT MnO2. If you do this in an acidic medium, for example in H2SO4, you're just going to get decolorization of your purple KMnO4. No brown PPT. And yes, this is a very good distinguishing test for alkenes because this reaction, this mild oxidation reaction is very unique to alkenes. No other chemical group, no other functional group can go through this reaction. Under oxidation, a very strong oxidation reaction is called oxidative cleavage. Now, under a hot temperature, with KMnO4 and in an acidic medium for example, what's going to happen is you're going to break the whole double bond itself and you can form a variety of products depending on a few conditions. So how I would know the different products that comes out from oxidative cleavage is I would first split open the double bond, and from here you can actually get two products already. Now depending on what A and B are or what D and E are here, this is how you would predict the different products that come about. So in scenario 1, if A and B are H and H, so it's only H's, this will automatically become CO2 and H2O. Now if there's one R group, you will get a carboxylic acid. The H will just become a OH. And then for scenario 3, if both are R groups, they're not going to be further oxidized and you're left with a ketone. Now for some special cases, if you see this ethane dioic acid, which is very popularly asked because it's a very common trap, this ethane dioic acid that will be formed from the reaction would just become CO2 and H2O. Same thing for your methanoic acid over here. Do take note of these two special cases. It's very often asked in exams. Lastly, for chemical tests for alkenes, we've run through a couple of different reactions. So some examples are adding your bromine in CCl4 or aqueous bromine itself, and you will get decolorization of orange bromine in your reaction, or you can do the oxidation with KMnO4. and you would get decolorization of your purple KMnO4. So you must know all these observations because it's important to state them very clearly in your distinguishing test. And that's it for alkenes. Remember, it's important to memorize all your reagents and conditions as well as reaction mechanisms and all the reasonings behind the different aspects of your reactions. If you memorize these, you surely master the alkene topic. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. If you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past papers and go through any doubts and clarifications you need and show you why my course is the best fit for you. I'll see you in the next lesson.